All right, so we're starting off with isomers.
Okay.
Since we already know that isomers are all of those molecules that have the same molecular formula but different structural formulas. So let's just
Yeah.
write down this definition in form of these points. So same molecular formula but different structural formula. Structural formulas are different because of the different connectivities here. For example, a pretty straightforward molecular formula is C4H10. This is a butane molecule, an alkane here. If you want to,
Okay.
let's say, draw a butane in its displayed structural formula, so a displayed formula of butane would be 4 carbons connected and then all of these hydrogens across these carbons. C4H10, yeah. So this is one way to write this structural formula here. Another way to write the same structural formula is to maybe add some branches. Instead of writing this main chain here in form of these 4 carbons, you could simply write these 3 carbons as main chain and then add the 4th carbon to the second carbon. And if you add all of these
Okay.
remaining hydrogens to this compound here, technically the molecular formula here is still the same, but the structural formula is different. So both of these two compounds here, although if you look at this, I mean, let me circle this. This is the first structure and this is the second structure here. So the first structure and the
Okay.
second structure here are both butanes. They exactly have 4 carbons and 10 hydrogens. You can even count the hydrogen in this one here. So C4H10
Okay.
is the molecular formula, but the structural formulas are different. Why? Because the connectivities are different. In the second compound here, this last carbon, which is placed alongside the 3rd carbon in the first structure, whereas if you look at the second structure here, this 4th carbon is placed right along with the second carbon and not the third one. So what we did
Okay.
here was we simply altered the connection and we placed this carbon next to another carbon here. So by this, we actually were changing the connectivities of these carbon atoms here. And by that, we achieved different structure. So this is why these two compounds, 1 and 2, are known as isomers of each other. All right. There's one thing to note here that if a molecule is flipped or
Okay.
twisted, it is not called an isomer. So flipped or twisted compounds are not isomers.
If they are what?
If the compounds are flipped or
All
twisted,
right. Okay.
they're not isomers. For example, so flipped or twisted compounds are basically same as compounds and mirror effects. For example, let's say if I okay, if you look at this one here, this second compound, if
Yeah.
we place a mirror over here, so the same compound in a mirror effect would look something like this. This CH3 would go on top and the remaining 3 carbons on bottom. So this is how this compound would look if you place a mirror on top of it. So
Okay.
technically, okay, let's say this is this third compound here. So compound 2 and compound 3 are not isomers, although they do have same molecular formulas, they have different structural formulas, but the structural formula difference that we have here is because of the mirror effect here. The compound is just getting flipped. There's no technical difference between the connectivities. So the
All right.
thing I
Okay.
was explaining earlier regarding the connectivities was very important, that in order to change the structural formula, it's important for you to alter the connectivity, not just flip it or twist it, because that I mean, because of flipping or twisting a compound, you won't be creating any other isomer. In fact, the compound will still be the same. All right. Let me give you
Okay.
another example regarding these exceptions there. Let's say if we have a compound here, CH3, C double bond OH. Now, this is, let's say, compound number 1. If, let's say, we um, rotate this compound to a different angle, in that case, what if we take this OH and place it on this side here? these dotted compounds are all the rotated positions that we can achieve by moving these original connections. Or we could and we can we can also rotate this entire compound to 90 degrees here. By doing so, the new compound that we get is CH3 on top. So see how if we rotate this original compound 90 degrees, this will be the new one here. So technically what we did was we simply changed the position of this OH bond. We placed it on the other side of this carbon, and we flipped we rotated this entire compound to an angle of 90 degrees. By doing so, we didn't actually alter any connectivity here. If you notice closely, this OH is connected to this carbon. This OH is still connected to this carbon. I mean, if it's, let's say, connected on right side, on left side, that doesn't matter as far as it's connected to that original carbon. Similarly, if you look at the other connectivities here, this CH3, this entire part CH3 is connected to this, let's say, chiral carbon here. I'm going to make a star here. And again, this is the carbon with a star, and this entire CH3 is connected to that same carbon. So we haven't altered any connectivity. We've just rotated the entire compound to an angle. And even in the case of this rotation of OH, we were just changing the side of this OH bond. We weren't actually changing the connection. How would this classify as an isomer if I would have picked up this OH and placed it with this and hydrogen with this? Now this would classify as isomer. But if we weren't really altering any bond, any connection. So this is why these two compounds here are also not isomers. I'm going to put a cross here. These are not isomers here. These are just rotated and flipped versions of each other.
Okay.
The same example, but with a correct positioning and formation of isomer. For example, let's say CH3COH. If let's say we were asked to make an isomer of this compound here. So what we can do is we can break this oxygen. We can put this oxygen with this hydrogen, and we can let this hydrogen stay as it is. So now in this case, the new compound that we'll get is CH2OH, because we've taken this oxygen and placed it with this hydrogen, C double bond O and H. So now if you notice, this is a different compound and this is a different compound. Why? Because oxygen in compound number 1 was connected to this carbon with a star, whereas oxygen in compound number 2 is connected to the other carbon here. So now we've altered the connectivity. So this is why 1 and 2 are isomers of each other. So they classify as isomers.
Right. Okay.
So, and then what type of isomers do we get? What are the names for these isomers? This is what we study further after this. Classification of isomers based on these connections. There are two major types of isomers. Number one, the structural isomers.
Okay.
And number two, stereoisomers. There are further three types of structural isomers here. Number one, positional. Number two, chain or branch isomers.
Okay.
And number three, functional group isomers.
Right.
There are further two types of stereoisomers as well. Number one, optical isomers, and geometric isomers. So let's discuss these types further. For positional isomers here. So positional isomers are all the isomers where the position of an alkyl group or the position of a functional group is changed.
Okay.
Position of alkyl group is basically a carbon group. Okay. Example, it's also denoted by an R, or for example, a CHX denotes any number of hydrogens. Any carbon chain is basically an alkyl group. So position of alkyl group or functional group is changed. This is what if positional isomer is. So let's look at an example here. For example, if you have these 4 carbons and OH at the end. I mean, this is an example
Okay.
similar to what we were trying to do earlier. If
Yeah.
you break this and you change the position, um, if you change the carbon here and you place OH on another carbon, this is a positional isomer here, because the hydro OH group is attached to different alkyl chains, different carbons here. So we are technically changing the position of a functional group. Whereas if you look at an exception here, for example,
Yeah.
what will not classify as an isomer, 4 carbons and OH here, or a mirror version for the same one. So if you look at these two here, both of these are exactly the flipped versions of each other. Because in
Yeah.
organic chemistry, we've studied that we start counting, we can count from either side. That's up to us. This could be carbon 1, carbon 2, carbon 3, carbon 4, or this could
Yeah.
be carbon 1, carbon 2, carbon 3, carbon 4. So if we say
Okay.
that OH is attached on second carbon from this side, and if you start counting from the left-hand side to the second compound here, 1, 2, 3, 4, so OH is also attached on the second carbon in the second compound as well. So technically, this OH is attached on the same carbons in both of these compounds. This is why
Yeah.
these are not the isomers. Okay.
All right. Okay.
Now, chain or branch isomers. Chain or branch isomers are all those where a carbon chain is altered.
Okay. Okay.
For example, for 5 carbons here, and let's say add another carbon, and now this 5th carbon is attached on the 3rd carbon here, the carbon chain is broken. Initially in the first compound, there was a main chain of 5 carbons, but in the second
Okay.
molecule here, the main chain only has 4 carbons, and there is 1 branched carbon here. So now this is, I mean, these are known as chain or branch isomers. But if we look at an exception here, okay, now if you look at these two compounds, in the first
Okay.
compound, the main chain is 1, 2, 3, 4. 1, 2, 3, 4, 5. Sorry, these 5 carbons, this is a main chain, and this one is a branch chain. All right, this is
Okay.
one way of looking at this compound. The other way is if you consider the straight chain as the main chain. This is the main chain, and this is the branch.
Yeah.
Either way, your main chain has 5 carbons, and your branch has 1 carbon. But if you look at the second compound here, 1, 2, 3, 4, 5. Again, the main chain has 5 carbons, and
Yeah.
there's 1 branch. So technically, I mean, if you look at these two compounds, they have different shapes. They are maybe flipped or rotated, but the connections are exactly the same. So this is why both of these are not isomers of each other. Right?
Okay. Yeah.
Right.
I mean, wouldn't you call them position? I mean, because the position of the carbons are moved around there.
No, we haven't really moved any position of the carbons here as well. We've just bended that compound. If you look at the position isomer here, we actually, okay, I mean, look at this here. The branch was attached onto the 4th carbon here, right?
Yeah.
Yeah, onto the 4th carbon. Okay, don't, okay, forget that. Look at the main chains here. 1, 2, 3, 4, 5, 5 carbons in a main chain and 5 carbons in a main chain on the second compound as well, and 1 branch. Whereas if you look at this positional isomer here, the carbon chain, sorry, the branch that's connected onto the main chain, it's
Yeah.
connected onto a different carbon here. Now what you can do is for this compound here, the first one, you can also write it like 4 carbons here, fifth, or like this maybe. In either way, you're just changing
Okay.
these bends. You're not altering any carbon position, not the position exactly, the connectivity here. If we, let's say, look
Okay.
at this one here, what we can do is, this is 1, 2, 3, 4, and 5 here. Okay, yeah, look at this. This is, I mean, both of these will classify as the same compounds here. Now, see, 2 carbons here, 2 carbons here, but I simply change the positions without altering the connectivities. Okay, so this is very
Okay.
important to understand the difference here. That these bended, I mean, always, I mean, don't just get confused in the shapes, because these names are pretty similar, the criteria are pretty similar, position, branch, isomers. So the only perfect trick to distinguish between these types of isomers is to look at the main chain first of all, and the branches. That is going to help you. If, let's say, in both of these compounds, the main chain has the same number of carbons and the branch chain also has the same number of carbons, then they're not the isomers. Keeping in
Yeah.
mind the connectivities, okay?
Yeah.
All right. Let's look at the functional group isomers now. Functional group isomers are those isomers when a functional group is changed or broken or altered in any way. For example, this is an alcohol here. One way
Yeah.
to do it is, okay, assuming there are all these hydrogens on these sides. This is an example that we did earlier as well. If you break this oxygen and place it onto another
Okay.
on another, let's not the same carbon, of course, on another carbon, that is how you'll make another functional group isomer. Or what you can do is you can simply pick this oxygen and put it in the center of this chain. So that way you're going to obtain a chain with 2 carbons, an oxygen and another carbon, and all these hydrogen on the other sides. This is another compound, okay?
Okay.
Whereas this is a completely different compound. You see, this is hydroxyl group here, whereas we have broken this hydroxyl group for the second compound, right? So you're
Yeah.
allowed to do this as well. You can break the functional group completely. Okay.
Okay.
Most of these functional group isomers exist between carboxylic acids and esters, aldehydes and ketones, alcohols and carboxylic acids. Okay, these are the compounds that
Okay.
we generally alter to create these functional group isomers. Yeah, let me just write it here. These common isomers as well. All these alkenes and cycloalkenes are usually these chain isomers of each other. You can even experiment with these compounds. So alkenes, you'll study these cycloalkenes in the year 2 syllabus. So then you'll understand how these two functional groups are exactly chain isomers of each other's.
Okay.
All these aldehydes and ketones are positional isomers. Carboxylic acids and esters are functional group isomers.
Okay.
what we can do now is you can maybe take a screenshot of the board, or if you want to write down the notes, you can. I'll give you a few minutes to do that. We're done with structural isomers there. We're yet to do
Right. Yeah.
stereoisomers. So these were all the three types of structural isomers and their examples. You can practice similar examples by breaking and making these compounds.
Okay. Yeah. Copied it down.
All right. Optical isomers now. So stereoisomers, let's just look at a definition for stereoisomers. Basically, yes, they have the same molecular formulas, the structural formulas. Okay, now in this case, the structural formulas are also same, but the arrangement of atoms is different.
Okay.
Same molecular formulas. Same structural formulas. Different arrangement of atoms. Okay, optical isomers are all those isomers having a chiral carbon. A chiral carbon is basically a carbon that's connected to 4 different single bonds. So chiral carbon connected to 4 different and single bonds. For example,
Okay.
carbon connected to OH, connected to another carbon, connected to hydrogen, connected to another carbon having C double bond OH. Okay. So now this central carbon here, this one, it's connected to OH on one side. It's connected to C double bond OH on the other side. It's connected to CH3 on one side and H on one side. So this carbon, the central carbon has 4 different bonds and 4 single bonds. This is known as a chiral carbon. Now,
Okay.
optical isomers are all those molecules having a chiral carbon that is flipped as a mirror image now. For example, this is your chiral carbon connected to CH3, then to CH2, CH3 connected to
Right.
Cl and hydrogen. The same carbon, let's say if you flip this entire compound in a mirror, this is how the mirrored version would look like.
Okay.
No, sorry, this has to be in the same direction, CH2 and CH3. Yeah. Okay. So now these two are optical isomers. One combination, I mean, one chiral carbon can have two combinations, because see, if we had one chiral carbon and we got two isomers.
Okay.
Similarly, two
Yeah.
chiral carbons will produce four combinations. The general formula is 2 raised to the power of n. N is the number of chiral carbons. 2 is a constant here.
Okay.
For example, 2 raised to the power of 1 will get 2. So 2 isomers, 2 raised to the power of 2, 4 combinations, 2 raised to the power of 3, 8 combinations. Okay. This is how the combinations would vary depending on the number of chiral carbons, and you can simply use this formula to get the number of combinations produced. Now,
Okay.
geometric isomers. I'm gonna write down the description here. Okay. Geometric isomers are all those isomers having a carbon to carbon double bond, first of all, and when that double bond is bonded to two different groups on different sides. Carbon to
Okay.
carbon double bond bonded to two different groups. If both the groups are if both the similar groups, sorry, face the same side, they are known as cis isomers, otherwise trans isomers. Example, carbon to carbon double bond here. Now this carbon has a hydrogen on one side and the second one also has a hydrogen. The second one has a chlorine on the other side and the first one has CH2 on the other side. So now it has three different bonds connected here. What we can do is we can alter these positions. We can bring this hydrogen down and take the CH2 up. So that way we're gonna have, we were simply altering the position of these two, and we can let the first one remain as it is. This way, if you look at the first compound here, it has both of the hydrogens on the same side, this upper side, whereas the second one has these hydrogens on different sides, one on the upper side and one on the lower side. This is why the first one is known as a cis isomer and the second one is known as a trans isomer. For a cis isomer, the two similar compounds, the two similar atoms must face the same side. For a trans isomer, the two similar atoms must face different sides. The two hydrogens here are facing different sides, whereas in a cis isomer, the two hydrogens here are facing the same side. All right.
Okay.
And number of combinations, again, you can guess the number of combinations by using 2 raised to the power of n. N here is the number of double bonds. One double bond will give you 2 combinations. 2 double bonds will give you 4, and so on. All right. Similarly, in symmetric molecules,
Okay.
this one here was a symmetric molecule here. The cis trans and trans cis are exactly the same. I'm going to give you an example of the second, you could say this type, where there are 2 double bonds producing 4 combinations. This could be, let's say, carbon to carbon and then another carbon to carbon.
Okay.
So let's say if there's a hydrogen on one side and there's another hydrogen and Cl, hydrogen 1, 2, hydrogen and Cl. Okay. If you notice, the first double bond here, the first part where there's a double bond, the hydrogens are on the same side, whereas on the same compound, the second part, the second double bond, the hydrogen on the different sides. So this is known as a cis trans compound. What we can do is, let's make an isomer But what we're gonna do is, for the first one here, we'll place chlorine on the upper side and hydrogen on this lower side. And for this one, we're gonna again, yeah, flip chlorine on the upper side, hydrogen lower side. So if you look at this example here, for the first one, hydrogen is on different sides, right? And for the
Yeah.
second one, the hydrogen is on the same side. So now this is a trans cis compound. First one was a cis trans compound, and this is a trans cis compound. The
Okay.
both of these two compounds are the same thing. They're not isomers of each other. I mean, now you can guess why, because we've just simply flipped the positions of these compounds. Yeah. If you, let's say, bring
Yeah.
this compound up and take this down, you're going to get exactly the same thing as the first one. So this is why cis trans and trans cis in symmetric compounds are classified as one single compound. Symmetric compounds where there's a symmetry in between. These were symmetric compounds. Both of these were symmetric. Okay. So we're gonna write this note here that cis trans. The reason for telling this to you is because at times you'll be asked to guess the number of isomers for a particular compound in form of MCQs.
Okay.
They'll ask you whether this compound will produce 2 isomers, 3 or 4. So what students do, I mean, for example, if you look at this, the same example, you can have a cis/cis compound, you can have a cis/trans, you can have a trans/cis, and you can have a trans/trans as well. But there will be a total of 3 isomers: number 1, number 2, and number 3. Students usually write this as 4 isomers. That is wrong, because the 2 over here are exactly the same compounds. This is why a combination of symmetric molecules will produce only 3 combinations, not 4. This is where you cannot follow this 2 raised to the power of n technique. This 2 raised to the power n technique is only followed for asymmetric compounds. So cis trans and trans cis are classified as a single compound or a single isomer for symmetric molecules. I hope this is clear.
Yeah.
Okay, perfect. And we're done with the topic here.
Okay.